Dear students, welcome to the second session of our chapter 8 Redox Reactions. Today we will start the topic with Stokes notation. It is the notation used where the oxidation state of the element is represented by Roman numerals. Like if we are having a chemical formula FeO and we have to see that the ion is in which oxidation state. So how we are getting the oxidation state? If we want the ions oxidation state, put the ions oxidation state be X plus the other one is oxygen 1 into minus 2 is equal to 0, and we are getting what Fe as plus 2 oxidation state. So the plus 2 oxidation state can be represented by the Roman numeral for ion. So how we can write the notation, Stokes notation? Fe, in the parenthesis we are writing the Roman 2O. This represents the ion is in plus 2 oxidation state. Same way Fe2O3, the ion is in third oxidation state or plus 3 oxidation state. By seeing the formula we can understand Fe parenthesis and Roman numeral 3O it is written. That means it is having a plus 3 oxidation state. For CuO, the oxidation state for copper is plus 2. That's why in Roman numeral 2 is mentioned. Cu2O plus 1 oxidation state. So this is about the Stokes notation. So how we are writing? According to the metals oxidation state, we are representing the Stokes notation by Roman numerals in the parenthesis. Next topic is the different types of redox reactions. We are having 4 different types of redox reactions. First one, combination reaction, decomposition reaction, displacement reaction, and disproportionation reactions. So these are the 4 different types of redox reactions. And as we know that redox reaction is the oxidation and reduction simultaneously occurring in the reaction is said to be redox. Let's see the first one, combination reactions. A combination reaction may be denoted in the manner like A plus B giving C. That means A and B are the reactants and it combines to give you a single product. It is said to be combination reaction. Either A and B or both A and B must be in the elemental form for such a reaction to be redox reaction. So what condition we are having in this redox reaction? In the combination reaction of redox, either one of the reactant or both the reactants should be in a elemental form. That means their oxidation state will be 0. Either one or both reactants. All the combustion reactions which make use of elemental dioxygen or oxygen as well as other reactions involving the elements other than dioxygen are called redox reactions. And some of the examples like carbon plus oxygen, we can see here the dioxygen is there, which is the elemental form. Its oxidation state is 0. Carbon as well, here it's in the 0 oxidation state, and these two after the combustion we are getting what? Carbon dioxide. So this is what an example of combination reaction. Another one is like magnesium. It's in magnesium in elemental form, nitrogen gas in elemental form, and these two combine and gives you magnesium nitride. That means how we have explained the combination reaction, either of the two reactant or both of them, if they are in the elemental form and combines to give a product, it is said to be a redox reaction. It is said to be a redox reaction. The second type of redox reaction is decomposition reactions. It is the opposite of combination reaction. A decomposition reaction leads to the breakdown of a compound into two or more components. And that time also we are having a condition that at least one of which must be in the elemental state. Like 2H2, this is the decomposition of water. It gives you 2H2 plus oxygen. Here you can see the breakdown is there for the water molecule. And after breakdown, we are getting two hydrogen and one oxygen molecule, and they are in elemental forms. So this is a decomposition reaction. 2NaH, sodium hydride, gives you sodium plus hydrogen, elemental forms. Then 2KClO3, potassium chlorate, 2KCl plus 3O2, and in this oxygen is in elemental form. So you can understand that when the decomposition reaction is there, it breaks down, or the compound is break down to give two or more components with at least one in the elemental form. This is said to be decomposition reaction of redox reaction. Now the third one is displacement reaction. With the name itself, we know that something is going to displace the other one. And in a displacement reaction, ion, an ion or an atom in a compound is replaced by an atom or ion of the other element. It may be represented in the general form x plus yz, giving xz plus y. And here you can see the y has been, or x has displaced the y, and the combination is xz. So this is said to be displacement reaction, and it fits into two categories, that is metal displacement and non-metal displacement reaction. Now let's see the first type of displacement reaction, that is metal displacement reaction. A metal in a compound can be displaced by another metal in the uncombined state. So this is what about the displacement reaction of a redox reaction. Now let's see one example like vanadium pentoxide. When it reacts with calcium, the displacement is between vanadium and calcium and gives you calcium oxide plus vanadium. Here both the oxidation as well as the reduction is taking place. That's why it's a redox reaction. The second example here we can see here, titanium tetrachloride plus magnesium gives you titanium plus magnesium chloride. That means the metal has been displaced. That is titanium. Magnesium displaces the titanium and forms magnesium chloride. And in each case, the reducing metal is better reducing agent than the one that is being reduced. Why? Because it shows more capability to lose the electron as compared to one that is reduced. The next type is the non-metal displacement. The non-metal displacement redox reactions include hydrogen displacement and are rarely occurring reactions involving oxygen displacement. All the alkali metals and some alkaline earth metals like calcium, strontium and barium with a very good reductance will displace hydrogen from the cold water, like sodium plus water giving sodium hydroxide plus hydrogen. Calcium plus water gives you calcium hydroxide plus hydrogen. So there's a non-metal which displays, or in this non-metal displacement, the hydrogen displacement is there. From this water, the hydrogen has been taken out, or it is displaced and forms hydrogen hydroxide as well as hydrogen gas. So this is the third type of redox reaction. And the last one is disproportionation reaction. And it is a special type of redox reaction. And in this type of redox reaction, an element in one oxidation state is simultaneously oxidized and reduced. But one more condition is there, that is, one of the reacting substance in this reaction always contain an element that can exist in at least three oxidation states. The element will be having three oxidation state in the single reaction. The element in the form of reacting substance is in the intermediate oxidation state. That is, both higher and lower oxidation state of that element are formed in the reaction. Let's see one example of hydrogen peroxide. When it decomposes, you will get what? Water molecule plus oxygen. You can see here the hydrogen in hydrogen peroxide is having an oxidation state of +1, whereas the peroxide in peroxide oxygen is having -1 oxidation state. When it decomposes the water, hydrogen will be +1 oxidation state, oxygen -2, and the oxygen gas is having the elemental state, that is zero oxidation state. So what we can understand with this reaction is hydrogen is having plus one oxidation state only, but there's a one element, that is oxygen is there, which has two more oxidation states, that is total three oxidation states it has, that is minus 1, minus 2, 0. So what is the normal oxidation state of oxygen? That is minus 2. One is lower and one is higher oxidation state. Like that we will get. So in a single reaction, if we are having the single element in three different oxidation state, we can name it as disproportionation reaction. And in one more thing we can understand, that in the same reaction the oxidation as well as the reduction is done. The same element is being changed, that is from minus 1 to 0, from minus 1 to minus 2. So both oxidation as well as reduction has been taken place. The oxygen of peroxide, which is present in minus 1 state, is converted to 0 oxidation state in oxygen, whereas the decrease to minus 2 oxidation state in water. So we can understand through this, as at a time the oxidation as well as reduction is taking place in the disproportionation reaction. The only condition is the single element will be exhibiting three oxidation states. One is higher and the other one lower oxidation state is there. Thank you. We'll continue in the next session.